Hey, Algebra. I'm here today to cover section 7.1, the first section of chapter 7. Now, chapter 7 deals primarily with radicals, square roots, cube roots, fourth roots, things like that. But there are some basic kind of fundamentals that we have to cover and really hone in on before we get to those radicals. So that's what we're looking at today. We're looking at operations on functions. We're going to talk about adding, subtracting, multiplying, dividing, as well as a new one called function composition. So let's dive right in. I've given two functions, and these are just made up functions that I'm providing. F of x, which equals 3x squared minus 4, and g of x, which equals 17x plus 11. So the first thing you need to know about these function operations is when we are operating on functions, oftentimes you will see this shorthand used. And this shorthand looks like this. It says, what is f plus g of x? That looks a little funny. The f and the g, and you're like, are those variables? What does that mean? Well, the good news is it means all we're looking at is f of x plus g of x, that individual f of x that we know, plus that individual g of x that we know. So if I color code this, and I'm going to try to always write f of x in red and g of x in blue, then if I'm looking for f plus g of x, I'm really just looking for 3x squared minus 4, that was my f of x function I was given, plus 17x plus 11, my g of x function. And although we haven't added functions before necessarily, we definitely have added expressions. And so we can use those same rules. We can say, let's combine the like terms on this problem. X squareds, it looks like it's just those 3x squareds. It looks like it's just those 17x's, so plus 17x. But then let's combine the constants, -4 plus positive 11 plus 7. So f plus g of x, that's how we can add functions, just that new notation. Take your individual f, add your individual g, simplify, combine like terms, do the things you know how to do. If you're looking at the right-hand side of the screen, you can probably guess what's coming. What about subtraction? Well, exact same game. F minus g of x is the exact same as, I was on my pen, not my highlighter. Individual f of x minus individual g of x. So let's do this. Individual f of x was 3x squared minus 4 plus, sorry, we're subtracting now, minus 17x plus 11. So same thing, take your individual functions, let's combine those like terms. Be careful with that minus to distribute that minus. We have, it looks like 3x squareds minus 17x's. And then for the constant, we had -4 minus 11, which comes out to -15. 3x squared minus 17x minus 15. So adding and subtracting expressions, it's not the end of the world. So we've done it with expressions, sorry, I misspoke. Adding and subtracting functions from one another, not too bad. What about multiplying? What if we did some multiplying? F times g of x. You'll also sometimes see this written just as fg of x. But the good news is either one of those ways, however it's written, it's a new notation, but we can just break those pieces down into their individual functions. F of x times g of x. So I'll write down my f of x, which was 3x squared minus 4, times my g of x, which was 17x plus 11. And we know how to multiply two binomials. We're going to FOIL this. So 3x squared times 17x is 51x cubed plus 33x squared minus 4, so -4 times 17x minus 68x's minus 44. And there are no like terms there. There are no multiple x squareds or x cubes. So I'm just going to call it, and that's our answer. FOIL it out, multiply it out, combine anything if you can to simplify, but in this case we couldn't. It happens. So multiplying, also I would put in the category of somewhat familiar. We've done this before. Now, dividing has a little bit of a wrinkle. It's just something we always got to keep in our mind. So dividing will look like this: f over g, or f divided by g of x. And just like before, as you probably predicted, we can just take our f of x and divide it by our g of x. So f of x, okay, 3x squared minus 4 over my g of x, which was 17x plus 11. But I mentioned a wrinkle. There are certain rules in math that are just so important that you definitely don't want to break them. You definitely don't want anyone else to break them either. We are creating a new function when we are dividing these two, f divided by g. And as it turns out, there's a value that this will cause an error for. And so we have to do something called restricting the domain. Whenever we have function division, we have to think about restricting the domain. And here's what restricting the domain is. I'm going to try to give you an analogy and give you the understanding and then how to do it. Okay, so restricting the domain makes me think of Baby Groot. And specifically Baby Groot in that scene in Guardians of the Galaxy 2, if you've seen that movie, where Rocket is telling Baby Groot, definitely don't hit this button. And then Baby Groot, as you can see from below, is like, should I hit this button? And that's kind of what we're doing here. We are going to restrict the domain so that we never divide by 0. We're trying to provide safeguards so that we'll never divide by 0. That's the rule we don't want to break. And so we're going to make it just Baby Groot proof so that even Baby Groot knows, okay, so nope, I'm not going to divide by 0. We're going to say definitely don't plug in the wrong value. So f of x, here's my example. If we were working with x plus 7 over x minus 4, what value would be a problem for us to plug in that would cause us to divide by 0? Well, we could just take a look down here and say, what would make my denominator equal 0? And I'm going to put a slash through that equals. Because I want to say x minus 4 cannot equal 0. That would cause me to divide by 0. Bad things would happen. Well, if we add that 4 to the other side, that means x cannot equal 4. So to restrict the domain, after we divide, we're going to come over here and say, comma, x cannot equal 4. And that is us just guaranteeing, look, we're not letting you divide by 0 in this. This works for everything except x cannot equal 4. That's the one thing it won't work for. So hopefully that the why kind of makes a little bit of sense. Let's do it on this problem. We want to say, okay, 17x plus 11. We don't want to divide by 0, so I'm going to say 17x plus 11 cannot equal 0. So 17x cannot equal negative 11. X cannot equal negative 11 17ths. That is the value I need to restrict out of my domain. So to restrict that out of my domain, I'm just going to say, comma, x cannot equal negative 11 17ths. So whenever we have function division, we want to just keep that in mind, that we should always look to make sure we're not dividing by 0. Okay, so this is four good operation problems. What I want to do is I want to pick your brain and give you a little bit of practice. I want you to take those same two starting functions, f of x and g of x, and in a second, you're going to basically flip what we just did every time. You're going to do g plus f of x. You're going to do g minus f of x, g times f of x, and g divided by f of x. And here's my question that I want you to think about, and I want you to come up with an answer to this, a guess, before you start working these problems out. And here's what it is. Will switching the order make a difference for these operations? Will switching the order make a difference for addition or for subtraction or multiplication or division? So go ahead, pause this video. I'm going to pause mine, work these out, and then we will answer that question, just a conceptual question here once we both restart. Also work out the problems just to double check and get a little bit of practice with these function operations. All right, by now you've had a chance to work these problems. Let's take a look and let's talk about that conceptual question that I posed to you. Does the order matter for these operations? How I think about that conceptual question is, I just think about simple numbers. Is 2 plus 3 the same as 3 plus 2? The answer is yes. I mean, 2 plus 3 is the same as 3 plus 2. The order doesn't really matter. So when adding, it seems like the order doesn't matter. And sure enough, 3x squared plus 17x plus 7, that's the same thing we got with f plus g. Feeling good on that one. Subtracting, does order matter? Is 2 minus 3 the same as 3 minus 2? Well, no. I mean, 2 minus 3 is -1. 3 minus 2 is 1. And so looking there, I think this won't be the same. And sure enough, it's not the same. Some of those signs have flipped. So -3x squared plus 17x plus 15. I have a picture of baby Groot there just to remind us to check, was there any division going on? Because sometimes division can even go on inside of other operations. Fortunately for us here, the answer was no. So what about right here, g times f? Is 2 times 3 the same as 3 times 2? 6, yeah. So multiplication probably won't make a big difference. And sure enough, we got the same answer. There was no division involved, so no need to restrict the domain. And then dividing, and this one, the simplifying was a little bit tricky when restricting the domain. 2 divided by 3 is definitely different from 3 divided by 2. So yeah, so it's not going to be the same. I need to do this. I plugged in the g over the f. And when we're restricting the domain, couple key points I just want to review with you. X cannot equal, x squared, excuse me, cannot equal 4/3. Take the square root. Remember there's a plus or minus on that square root. And then remember that we can simplify a fraction by taking the square root at the top and the square root of the bottom individually. Now, if we end up with a radical in the denominator, we have to rationalize that denominator. I multiplied in green by √3 over √3 to get 2 √3 over 3. So this is our division problem. This is basically operations on functions. Of course, there are two kind of more difficult, I just want to throw you an extra wrinkle that these problems can have, going back to my previous statement about having division inside of other operations. So let's take a look at this problem. We're asked, what is r over s of t? And so that's r of t over s of t, and here's my r of t and my s of t. Now, straight out of the gate, if I were you, I would be factoring r of t, because it looks like something that could be factored. And I would say 8 times out of 10, we want it factored. So I'm just going to do this from the very beginning. I'm going to say, okay, so t squared minus t minus 6. Set up my parentheses, so t and t. This minus says that the signs are different, so plus and minus. And I need two numbers that multiply to be -6, add to be -1. I'm thinking those are -3, +2. So if you don't remember factoring, it's a really big deal and you're gonna wanna know how to do it. But I'm just gonna use that for my r of t because 8 times out of 10, like I said, I'm gonna want it factored. So the problem that was asked is, what is r of t over s of t? R of t I just factored was t minus 3 times t plus 2 over s of t, which was t minus 3 over t plus 2. Okay. Dividing, and there's a fraction inside that division. So how do we divide by a fraction? Copy dot flip. So I'm going to copy my numerator, t minus 3 times t plus 2 over 1 dot there with, for the denominator, because copy dot flip, we're going to multiply t plus 2 over t minus 3. And here's where the going gets good. We have a t minus 3 factor on top. We have a t minus 3 factor on bottom. Those are both gone. So we can say, okay, so we get t plus 2 times t plus 2 on top, multiplying straight across, over 1, just 1 on bottom. So I'm going to just FOIL that out, t squared plus 2t plus 2t, so plus 4t's plus 4 over 1. And anything over 1 is just itself, we know, so we'll just say t squared plus 4t plus 4. A baby Groot is sitting there lingering, waiting for us. Was there any division going on in this problem? The answer is yeah, there was a lot of division going on. We are going to have to restrict the domain and say, what can t not equal? So I'm going to come up here and I'm going to look for anywhere I had a fraction and just make sure that the denominator won't equal 0. So first fraction I see is right here. But the good news on that is 1 is not going to equal 0. I mean, it's just 1 down there. There's nothing I can plug in to make that equal 0 accidentally. So that one's fine. What about this right here? I need to make sure that that denominator doesn't equal 0. So t cannot equal -2, it looks like, because that would make that denominator 0. What about this one? Even though it canceled out, still got to consider it. T minus 3 on bottom, so t cannot equal 3. That would make it 0 on bottom. And those look like all the denominators we have. So we're going to say t cannot equal -2 or +3. So some division, some factoring, making these problems just a little bit harder. Let's look at one more for these operations. So I'm going to skip past the break because we're not in class right now, obviously. You can always take a break if you want while you're watching this video. R of t is t minus 3 times t plus 2 once we factored it, plus t minus 3 over t plus 2. How do we add fractions? Well, remember, we need to get them a common denominator. Right now they don't have that, so I'm going to multiply this left-hand one by t plus 2 on top and bottom, because now I will have a common denominator. We've done this before, we'll do it again. Let's see where it gets us. So on the left, I know I'm going to get t plus 2 on bottom, but I'd better start multiplying. So I'll FOIL out these first two, t squared minus 3t, but plus 2t. So minus t minus 6. And then we still haven't multiplied in this t plus 2 yet. And we're doing all of this so that we can add to this t minus 3 over t plus 2 over here on the side. So, okay, I got to multiply again on the left-hand side. So t cubed plus 2t squared minus t squared minus 2t minus 6t minus 12 over t plus 2 plus t minus 3 over t plus 2. Okay, simplify, and then we can, now that they have a common denominator, we'll be able to combine like terms. So t cubed, and then we have 2t squared minus t squared, so probably plus t squared minus 8t's, it looks like, minus 12 over t plus 2, plus t minus 3 over t plus 2. So let's figure out what this gives us at the end of the day. T cubed, looks like there's only that one t cubed at the beginning, only one t squared at the beginning. negative 8t's plus t from the blue looks like minus 7t's, negative 12 plus negative 3 minus 15 over t plus 2. So it looks like I think we've done our addition. Little bit of extra work because we had to get a common denominator, things like that, but we found our division. Only thing left to do because we were dividing is say what t cannot equal, not x. T cannot equal, and looking all through here, we've got a lot of t plus 2's on bottom. So what would cause that to be a problem and divide by 0 if t were negative 2? So we're going to say t cannot equal negative 2. So this is an overview of 4 operations, how we use them with functions, restricting the domain. Guys, I know it's going to be a little bit of a long video because it's a bit of a long section, but I'm going to keep going because there's one other operation that we need to know how to do with functions. And that is function composition. And the operator, instead of a plus sign or a times or something, it's this little open dot. And you see it there on the left-hand side of the screen. And what is that? How do we speak that? That is pronounced f of g of x. Now, before I tell you exactly what this is going to look like, I want to tell you my recommended first step for you. Anytime you have a composition problem, write it in this other notation, function notation, that has a little bit more meaning. F of g of x as it is written is the exact same as f of g of x. So I'm given 2 functions below, f of x and g of x. If I asked you what g of 10 was, you would probably tell me, oh, g of 10, that's not hard. G of 10, I'll just plug 10 in for x, 2 times 10, it's 20, right? If I asked you what f of 1 was, you would say, I'll just plug 1 in for x in my f function. So we're always plugging in whatever's inside the parentheses. Now here's the question. What's inside the parentheses? F of g of x. We're plugging one function into another here, which is kind of a new novel concept, but let me show you what it looks like. F of g of x, I'm going to write it in my notation because that reminds me, oh yeah, I'm going to work from the inside out and start plugging stuff in. So f of g of x, well, I know that g of x was 2x. It says it right up here. So really, I just need to plug in 2x. That's the same as plugging in g of x. So I'm plugging it into my f function. So I'm plugging 2x into my f function wherever I saw an x originally. And that means that I'm getting 7 times 4x squared, because I've applied that squared, plus 1. 28x squared plus 1. This is function composition. We are composing functions together by plugging one into the other. But take a look at those 4 lines that I wrote on the screen there. First, write it in your function notation. Then you know what g of x is. You're always going to start in the middle. Just swap out that 2x, plug it into your f function, and simplify. Let's try g of f of x, because we can absolutely kind of flip the order here. G of f of x would be g of f of x. So let's start in the middle. And so g was going to stay the same for a second, and f was 7x squared plus 1. That's what we were told right up there. So that's what I'm plugging into my g function. So let's do that. G function was 2 times whatever I'm plugging in, right? 2 times 7x squared plus 1 is looking like it'll give us a 14x squared plus 2 once I have distributed. That is g of f of x. So function composition, kind of a weird new thing, but we're going to practice it. We're going to run through a few examples, and then we will call it a day. I do have a note here, though, that if one of these functions had division in it, we would have to remember restricting the domain. Even though it's a new operation, we still got to remember that. But fortunately, there was no division, so we don't have to think about that step. So I've got those same two, f and g, up here on the screen. But now I'm going to add an h of x, just another thing for us to play with. So h of x is 4x plus 3. What is h of g of x? So following that same methodology, I'm going to say, okay, I'm going to write it as a function, h of g of x. So h of, and what was g of x? What do I need to plug in? H of 2x. So I need to plug that into my h function. 4 times whatever I'm plugging in plus 3, I'm plugging in 2x. So h of g of x looks like it'll be 8x plus 3. We're replacing that placeholder x in our h function with g of x, that function. Let's try this one, g of x. Can we plug something into itself? Why not? Why not? So I'm going to write it out. I'm going to say it's g of x. So g of start in the middle, and what was g of x? It was 2x. So I'm plugging 2x into my g function. Well, my g function was 2 times whatever I'm plugging in, right? So 2 times 2x, g of x in this case is 4x. Now we're going to look at a fun one right now. What about this? It's a triple, and it might look intimidating or look like just too much. As long as we take it one step at a time, we will be fine. We will be good to go. Let's write this in function notation. This is f of g of h of x. F of g of h of x. I've been saying we start in the middle. Let's do that. So I'm going to leave the outsides the same. F of g of, and what was h of x? It was 4x plus 3. So 4x plus 3. So start in the middle and replace that. Let's keep working our way inside out. So g of 4x plus 3, well, the g function is 2 times whatever I'm plugging in. So 2 times, I'm plugging in 4x plus 3. And so that'll give us 8x plus 6. Cool. So now I'm looking for f of 8x plus 6. Well, my f function was 7x squared plus 1. So 7 times whatever I'm plugging in squared plus 1. 8x plus 6. Okay, so a little bit of arithmetic here. I'm going to take care of that squared first. And remember, 8x plus 6 squared means 8x plus 6 times itself. So let's FOIL off to the side here. I'm getting 64x squared plus 48x plus another 48x plus 36. So 64x squared plus 96x plus 36. So I just like doing that off to the side sometimes. Keep my work on the left more orderly. 7 times that plus 1. 7 times 64x squared plus 96x plus 36. Time for a calculator, I think. 7 times 64x squared, 7 times 64 is 448. So 448x squareds, 7 times 96, 672, so plus 672x. 7 times 36 is 252. And then don't forget about your plus 1 on the end. So final answer, 448x squared plus 672x's plus 253. You might look at that problem and say, okay, that was a lot. That was really hard. I would say it's not any harder than what we were doing before. It is more. It is more because you have to do composition kind of these 3 times. But start in the middle. We figured out what h of x was. Then we figured out what g of that was. Then we figured out what f of that was. And the numbers got big, but the process stayed the same. And that's what I want you to really see. All right. Last bit for today. It's not always just going to be g of x or h of g of x. What if it's h of g of 3a? Not much changes, in all honesty. Sorry, that should have been purple. H of g of 3a. We're still going to start from the inside out. What is g of 3a? Well, h of the g function was 2 times whatever I'm plugging in. So 2 times 3a. So that means we're looking at h of 6a. And we can figure that out. Let's plug 6a into my h function. 4 times whatever I'm plugging in plus 3. So it looks like h of g of 3a will be 24a plus 3. And hopefully you see that it's nothing different really. All right, how about g of 0? G of 0, blue. G of 0. Start on the inside. What is g of 0? Well, g of 0 is 2 times 0, 2 times whatever we're plugging in, which happens to be 0. So what is g of 0? Well, g of 0 is 2 times whatever we're plugging in, which is 0, which happens to be 0. Kind of just a fun one, plugging g into itself. To close us out, I would challenge you to try the triple on the right-hand side of the screen. I'll kind of move over there. I would challenge you to try this on your own. Pause the video, try it, see if you're really getting this function composition business, and then unpause it when you are done. And now I'm going to start working it out. So f of g of h of 1. So f of g of, what is h of 1? Well, if we look back over there, we can say h of 1, if we plug 1 in there, 4 times 1 is 4 plus 3 is 7. H of 1 is just 7. Well, then what is g of 7? G of 7 is going to be 2 times 7, because that's what I'm plugging in. G of 7 would just be 14. What is f of 14? 7 times I'm plugging 14 in, so 7 times 14 squared plus 1. And that might be one for the calculator. 7 times 14 squared plus 1. 1373. Function composition. It's a whole new world. But it's just plugging functions into one another. Last thing I will say, we're done with problems, but again, just a conceptual kind of thing I want to point out is, if you know what, say, g of x is, and I ask you what g of 0 is, you could just plug 0 into that. And we've kind of seen that before in different contexts, but if I plugged 0 in there, I would get 4 times 0, which is 0, and that's exactly what it is down here. H of G of 3A, if I plugged 3A, go away keyboard. If I plugged in 3A into just my generic H of G of X, I would get 8 times 3A, so 24A plus 3, which is exactly what we got down here. And if I plugged 1 into my triple up top, I would also get 1373. So just something to keep an eye out for, and maybe that'll make your life easier one day, knowing that. But when do we use composition? Composition is actually used a lot more than you think. Any time that we do something and then take its result and use it to do something else. That's what we're doing with composition. So anytime we're talking about taxes or wages, how much money you're making, purchases, maybe something's on sale and we have to apply that and then apply tax, unit conversion in the sciences, computer programming, obviously that's one of the places my head goes, pre-calculus, calculus, obviously higher branches of math. So composition is definitely well worth figuring out and mastering. So I'm hoping that this introduction to composition, as well as all those function operations, was helpful, makes sense. I know it's a long lesson, so thank you for sticking with me. Try those practice problems out. Let me know if you have questions. Either reach out to me or bring it up next time in class, and I will see you then.